The Euler Totient function phi is defined as follows. So if n is a positive integer, phi of n is equal to the number of integers between 1 and n, so 1 less than or equal to I less than or equal to n, such that I and n are relatively prime. So the greatest common divisor between I and n is equal to 1. That's what it means to say I and n are relatively prime. And we're going to calculate some basic examples, and this video is a compendium of the basics on the Euler Totient function. We're going to make fancy theorems like the Euler product formula and Gauss's theorem trivial, and we're going to go through it in a very beginner oriented way. So first of all, let's calculate some examples of this. So phi of 1 is basically just going to equal to 1. The greatest common divisor with 1 and 1 is just 1. Okay, so phi of 1 is equal to 1, and 1 is a number relatively prime to 1 between 1 and 1. Let's do some more examples. Phi of 2 is also going to equal to 1 because 2 is not relatively prime to 2. Okay, so between 1 and 2 we only have 1, which is relatively prime to 2. Okay, the greatest common divisor of 1 and 2 is 1. We can keep going. We're going to get some interesting examples at later on. So phi of 3 is going to equal to 2 because 1 and 2 are both having a greatest common divisor with 3 equaling 1. Okay, there's no common factor between these and 3. But 3 of course has a common factor with itself, just 3 itself. Now we can keep going, we can look at 4. So phi of 4 is what are the numbers from 1 to 4 that are relatively prime to 4. So we're going to have basically 1 and 3. Okay, so it's going to be two numbers, so phi of 4 is 2. And the reason that you have only 1 and 3 is because 2 and 4 have a common divisor with 4. Okay, so 2 and 4 have both 2 as a common divisor with 4. So phi of 4 is 2. Phi of 5 is by the same reasoning as earlier because 5 is a prime number. So there are 4 numbers from 1 to 5 that are relatively prime to 5. Just 1 through 4. 1, 2, 3, and 4. So phi of 5 is equal to 4. Okay, so this is a general principle that we'll see. That if p is a prime number, so if you take p is a prime number, how many numbers from 1 through p are relatively prime to p? It's just going to be p minus 1. Okay, 1, 2, 3, 4 up to p minus 1, but p itself has a common divisor with p. So this is going to be phi of p is p minus 1 when p is a prime number. But let's calculate something slightly more interesting. Let's calculate phi of 10. What is phi of 10 going to be? Well, phi of 10 is the number of integers from 1 through 10 that are relatively prime to 10. And what's going to be cool, you want to watch till the end because I'm going to give you a closed formula for phi in the end for any number. You can just spit it out. If you know the number, you don't have to enumerate everything. So phi of 10, let's just try to enumerate everything. What are the numbers from 1 through 10 that are relatively prime to 10? Well, 1 and then 2 isn't. Okay, 2 has a common factor with 10. 3 is, 4 isn't. It has a common factor of 2. So all the even numbers are getting deleted. This is an important principle. Okay, 2, 4, 6, 8, 10 can't be included. 5 also cannot be included because 5 and 10 have a common factor. So 5 is also excluded. So you have 1, 3, 7, 9, and that's it. Okay, so phi of 10 is just going to equal to 4. Okay, so I'm just going to write this out. 1, 3, and 7, 9 were the numbers, and phi of 10 is going to equal to 4. Okay, so that's going to be phi of 10. And so we're going to actually now do some calculations with phi and calculate it steadily. Okay, we've calculated phi of prime numbers. Let's calculate phi of prime powers now. And I'm going to do that on this side of the board. Before we get a closed formula, our first destination will be the Euler's product formula for the Euler Totient function. So we've calculated phi of p. What about phi of p squared if p is a prime number? How do you calculate that? So we're going to get some insights while we do this. We're not just calculating it, we're paving the way for our theorems. So what are the numbers from 1 through p squared that are relatively prime to p? Well, it just should be a number that isn't divisible by p. So there are p squared numbers in total from 1 to p squared, and out of those, what are the multiples of p? You've got 1 times p, you've got 2 times p, all the way up to you've got p times p, which is p squared. These numbers are not going to be relatively prime to p squared, but everything else is going to be because it's not going to be divisible by p, and p is prime. We're using that heavily, so you just have to subtract these number of numbers. There are p of them because they are p multiples of p. So phi of p squared is p squared minus p. That's the number of integers from 1 to p squared that is relatively prime to p squared. Okay, and we can keep going with this. We can actually figure out what phi of p to the k is for any positive integer k. Phi of p to the k is going to be p to the k minus something. What are the numbers from 1 through p to the k that are relatively prime to p to the k? Well, all the multiples of p basically, because for a number to be relatively prime to p to the k, it should not be divisible by p, because if you take its prime factorization, it's not going to have a common divisor with p to the k if and only if p doesn't appear in that prime factorization. So we do not want it to be divisible by p. So again, the same idea, we look at 1 times p, 2 times p, all the way up to p to the k minus 1 times p. Those are all the multiples of p from 1 through p to the k. So you're just going to subtract p to the k minus p to the k minus 1. And that's a formula for the Euler Totient function for prime powers. We'd like to find it for anything like 100, 1,000, just random numbers. And that's what we're going to do using the Euler product formula. So what does the Euler product formula say? And it's a beautiful probabilistic interpretation. You're going to love this one. So I'm going to do it right now. The Euler product formula is the following interpretation of calculating phi of n. Okay, so imagine you have some n and you want to calculate phi of n. Okay, so think about what the prime factorization of n is going to be. Okay, so n is going to have some prime factors. Okay, so let's say p1, p2 up to pk. These are the prime factors dividing n. So this symbol means dividing. Okay, they are factors of n. So I'm going to write out these are the prime factors of n. Okay, so these are all prime numbers. And let's think about what it means for a number to be relatively prime through n using a similar idea that we did here. So what it means is that the number should not be divisible by any of these primes. So if we think about the following quantity, phi of n by n, right? This is the probability that a number from 1 through n is going to be relatively prime to n. Because the top represents all the numbers from 1 through n that are relatively prime to n. And the bottom represents the total number of numbers from 1 through n. So it is favorable outcomes divided by total number of outcomes. This is the probability that the greatest common divisor of I and n is equal to 1 if you have 1 less than or equal to I less than or equal to n. That's the probability we're trying to calculate. Now let's think about this. For a number to be relatively prime to n, it shouldn't be divisible by p1. What is the probability a number is indivisible by p1? Well, every p1th number from 1 through n is going to be divisible by p1 because p1 divides n, so p1 is evenly going into n. p1, 2p1, 3p1, etc. They're all divisible by n. So the probability a number is indivisible by p1 from 1 through n is 1 minus 1 over p1. 1 over p1 is the probability it's divisible by p1, and 1 minus that is the probability it's not. Now if we keep doing that, for a number to be relatively prime to n, we want to multiply. We want it to be indivisible by p1, which is this probability. Then we want it to be indivisible by p2, which is this probability, and so on, all the way up to 1 minus 1 over pk, so it is indivisible by pk. So this is going to be the probability a number from 1 through n is indivisible by all of these. You're multiplying the probabilities, it's indivisible by each of the prime factors, and you're getting the quantity phi of n divided by n. That is now going to give us a super cool formula for the Euler Totient function, and I'm going to write that down on this side of the board. And don't forget to drop a comment down below. Think about it, leave me any questions. I love engagement, and other people can also comment and discuss. So let's now use this to actually give a formula for phi of n. So phi of n is going to equal to n times that. Okay, so it's going to be n times the product p prime, so that p is dividing n of 1 minus 1 over p. Okay, it's 1 minus 1 over p, the product over all primes dividing n, which is what we have there. This is what is called the Euler product formula for the Euler Totient function. Doesn't it seem obvious? That's what I'm trying to do. I'm next going to give a closed formula for phi and prove Gauss's theorem, which looks quite complicated. We're going to make it trivial. Okay, so let's now understand this a little more to get a closed formula for phi. Okay, so with this, we're going to observe something very crucial about phi. Okay, the first thing we're going to observe is we can recover what we figured out for prime powers from this formula. Because if n is a power of a prime, n is equal to a power of a prime, it's always good to understand things again and again. That reinforces understanding. I'm not just trying to show you math, I'm trying to teach you math. So phi of p to the k is just going to equal to p to the k. There's a single prime factor dividing n, right? So it's the same argument we did earlier. You know, every pth number is going to be divisible by p. So it's 1 minus 1 over p times p to the k. And that is actually just going to equal to p to the k minus p to the k minus 1. So that's all well and good. But in fact, we can figure out what phi of n is going to be for any number n. We're going to do that on that side of the board. What we need as an input is the prime factorization of n. So if n is equal to p1 power a1, p2 power a2, all the way up to pk power ak, then what we need to do is we need to look at this, and we're going to observe something really cool. Look at the Euler product formula. It's going to tell us that phi of n is going to equal to n times the product as I, or let's say as j varies from 1 through k, of 1 minus 1 over pj. Okay, that's the product we're looking at, because the p1 through pk's are all the prime factors of n, so this is the Euler product formula. Now once we've got this, we can observe that n itself is a product of those powers, so we can write this as the product as j varies from 1 to k, n is the product of all the prime powers, so we can factor this in and say pj power aj times 1 minus 1 over pj. Right, I've just taken n as a product of prime powers and just put that in. It's also a product j varies from 1 to k of pj power aj, and just put corresponding factors in. And what's really cool now is this is actually just the product from j varies from 1 to k of phi of pj power aj. So notice that we found phi of n by simply multiplying phi of each of the prime powers that are in its factorization. So this is so beautiful that phi is what is called a multiplicative function. In the language of arithmetic functions in number theory, we say a function is multiplicative if you can do exactly this. You can find phi of n by simply multiplying out phi of all the prime power factors of n. And this gives us something cool. Let's have some fun with it. We've got this far, we've done the work. Let's actually calculate a couple of examples before going on to more beautiful theory. Okay? So first of all, if you like, we can just write this out even more explicitly. Using what we know about prime powers, we can write this as phi of n is going to equal to p1 power a1 minus p1 power a1 minus 1 dot 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 the product over all primes dividing n of pk power ak minus pk power ak minus 1. Okay, that's going to be the product we're going to get for phi of n, and let's just figure out something simple. Let's figure out phi of 100. Okay, pretty cool. Imagine at the beginning, it's always cool to see in math how far you've come. In the beginning of this video, finding this and enumerating all the numbers from 1 through 100 and calculating how many of them are relatively prime to 100 seems very unwieldy. But now we just know the prime factorization of 100. Well, we know it's going to be 25 times 4, which is 2 squared times 5 squared. So we can just do this, which is then going to be phi of 2 squared times phi of 5 squared. And now we're almost done. This is going to be 2 squared minus 2 times 5 squared minus 5. And now that's going to just be 20 times 2. So it's going to equal to 40. Pretty cool, right? We just found out what phi of 100 is. Now I'm going to show you a little bit more theory before we get to Gauss's theorem. Okay? Or actually, we can just get to Gauss's theorem right now, which is going to blow your mind. Okay? So watch till the end to really digest this theorem. Gauss's theorem tells us the following. Gauss's theorem tells us the following. So this is a theorem that the sum as d divides n, the sum over all the divisors of n of phi of d is actually just going to equal to n. This is a beautiful theorem. It's a beautiful theorem, and it just looks not obvious from there. It just looks like you're adding up phi of d over all divisors of n. We don't really know what they look like, and they all somehow add up to n. So we're going to prove this theorem using theoretical math reasoning and using our understanding of phi as a multiplicative function. So as with any theorem, it's always important to think about special cases before proving it. You observe these kinds of results through special cases and get ideas for why they're true. So let's figure out what this looks like for a prime number. What if n is prime? Okay, so step 1 is what if n is a prime number, and then we'll get to prime powers and then figure out how to do the general case. So for prime numbers, we can just observe that what the left-hand side is going to tell us, it's going to be phi of 1 plus phi of p. Right? 1 and p are the divisors of p if p is prime. So generally, p denotes a prime number in math, so we say p is prime. We want to show that this is equal to p. Well, we know that phi of 1 is equal to 1, and we also know that phi of p is equal to p minus 1. Okay, there are p minus 1 numbers from 1 through p relatively prime through p. Just to reiterate, p itself is not. Okay, so we're just going to get 1 plus p minus 1, which is going to equal to p. So that's going to be true. For p prime, Gauss's theorem is true. What about for prime powers? Well, let's find out. This is going to look so beautiful for prime powers. I'm going to do it right here. Let's check out Gauss's theorem for prime powers. So what we can do is now we can say, what about the sum d divides p to the k? Okay, so for a power of a prime p, what is sum d divides p to the k of phi of d equal to? Well, we want it to equal to p to the k, but is it? So let's find out. So we just add up over all the divisors of p to the k. So we've got phi of 1 plus phi of p plus phi of p squared. So you keep on going all the way up to phi of p to the k. Okay? So far, let's see what happens. We have to see what happens when you add this all up. So phi of 1 is 1, phi of p is p minus 1, right? So we keep going. Phi of p squared is p squared minus p. Again, to reiterate, the number of multiples of p from 1 through p squared, there are p of them. So we just have to subtract them off to get the numbers relatively prime to p squared. Seen this calculation a few times, but it's good to keep reinforcing. P squared minus p, then you get p cubed minus p squared. Again, there are p squared multiples of p from 1 through p cubed, but eliminate them to find phi of p cubed. And you keep going all the way up to p to the k minus p to the k minus 1. And you see something really beautiful here. I'm just going to show it to you in red markers. I love doing this when you're doing math calculations. 1 cancels, minus 1, p cancels, minus p squared cancels, minus p squared. It keeps on going all the way up to p to the k minus 1, minus of that cancels, and we actually just end up with p to the k, and that is Gauss's theorem for prime powers. But now we have to prove Gauss's theorem for all numbers. How are we going to do that? So we're going to use some theoretical structure here, which is the idea that phi is a multiplicative function. So I'm going to talk a little bit about that and then get Gauss's theorem out of the way. So let's do that. All right, so multiplicative functions are the following. I already talked about it, but we say a function is an arithmetic function is a function from n to c. There's a bit of terminology to show you. So Euler Totient function is an arithmetic function. In fact, its range is just natural numbers, okay, or it's contained in the natural numbers. Okay, it's not necessarily complex numbers, but now what we can do is we can talk about multiplicative functions. So it has the following property that if n and m are co-prime, relatively prime, their greatest common divisor is 1, then phi splits up. So phi of nm is equal to phi of n times phi of m if the GCD of n and m is going to equal to 1. Okay, so that's a fundamental property of phi. And I'm going to use this structural property to prove Gauss's theorem. But what we want to do is why is this true first of all? Well, it's basically what we just saw. If n is a product of prime powers, p1 power a1 all the way up to pk power ak, and if m is a product of prime powers, q1 power b1 ql power bl, then because the greatest common divisor of n and m is 1, there's not going to be any common overlap in the prime factors of n and the prime factors of m. So in particular, we can calculate phi of nm. We just saw earlier in the proof, we saw that this was just equal to phi of the product p1 power a1 pk power ak all the way up to q1 power b1 ql power bl. And what we saw in the proof is that now we can split it up. We can do it prime power by prime power. So let's do it on this side of the board now. So prime power by prime power, this is just going to equal to phi of nm is just going to equal to phi of p1 power a1, so times phi of pk power ak multiplied phi of q1 power b1 all the way up to phi of ql power bl. Okay, so we're just multiplying it out, and then of course we know the first branch is equal to phi of n. By the same principle, we can just find phi of n by multiplying over the prime powers that are going into n, and then we get this is going to equal to phi of n times phi of m. So we've shown that it splits over co-prime numbers, and this is what it means to be a multiplicative function. However, it is not completely multiplicative. This is not true if n and m are not co-prime. As a simple example, if you wanted to find out phi of p squared, it's not going to equal to phi of p times phi of p. If it did, then perhaps a lot of number theory would be very, very easy. So unfortunately, that's not true because the left-hand side is p squared minus p, and the right-hand side is p minus 1 times p minus 1, which is p minus 1 squared. These are not equal, but that's fine. We can still use this property to now prove Gauss's theorem. So let me do that on this side of the board now. The first claim is we've proven Gauss's theorem. We've proven that sum d divides n of phi of d. Let's call this f of n. Okay, it's a new function. What we want to do is we want to prove that f of n is equal to n. Okay, we want to prove that this is equal to n, so I'm just going to put this in red here. We want to prove that this is equal to n. We don't know much about f of n yet, but we know some information. What do we know? We know that f of a prime power is equal to that prime power. That is, f of n is equal to n when n is a prime power, because we verified Gauss's theorem when n was a prime power. So we know that f of p to the k is just going to equal to p to the k. So that's tick. Now I claim that f is actually a multiplicative function, and this is where the whole theory is coming in. F is a multiplicative function, and why is that? Well, it's so beautiful. It's just a nice structural proof. So if we wanted to find out what is f of n times m, I'm going to do it on the right side of the board because I'm running out of space, and after this we're going to see Gauss's theorem in a beautiful way. This is real rigorous math. So let's calculate f of n times m. So we know that f of n times m by definition, this is what we want to find. It's going to be by definition of f, it's the sum as d divides nm of phi of d. But here's the cool thing. If n and m are co-prime, that's what multiplicative means, right? We have to think about when n and m are co-prime, we want to show f of nm is f of n times f of m. But when n and m are co-prime, what do divisors of nm look like? Well, n is a product of prime powers, p1 power a1 dot 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 pk power ak. And m is a product of prime powers, q1 power b1 dot 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 ql power bl. And if you think about a typical divisor of nm, it's going to have some part in this, in n, and some part in m. And it's going to be the product of its part in n times its part in m. Okay? So to be super precise about that, if d divides nm, you can write d as d prime times d double prime uniquely, where d prime divides n and d double prime divides m. Okay, you just take the prime powers that are dividing n that are in d, and then you take the prime powers dividing m that are in d, okay? And you multiply that out. So that means this sum is going to equal to the sum as d prime divides n, d double prime divides m of phi of d prime times d double prime. And now it's going to get really cool, because knowing that phi was multiplicative, which is what we proved, we know that we can split this up as the sum of phi of d times phi of d double prime. So we get d prime divides n of phi of d prime, d double prime, and d double prime divides m. And now we're almost there, because if we now use the fact that phi was multiplicative, I can actually do this in one step. We can get phi of d prime times phi of d double prime. And now we can write this out as two sums, a product of two sums. So I'm going to do that on the right side of the board. It's now going to equal to the sum as d prime divides n of phi of d prime multiplied by the sum as d double prime divides m of phi of d double prime. Okay? So we're going to get this product decomposition. And of course, this was going to equal to phi of n, f of n, and this was equal to f of m. So we've shown that f is multiplicative, and now we've proven Gauss's theorem. We've proven Gauss's theorem because we know that f of n is equal to n for all prime powers, and because f is multiplicative, we can now calculate f for any number. And I'm going to do that here, so I'm going to write that out here. We can now calculate that f of n was some d divides n of phi of d. We want to show it's equal to n. So we just note that f of any number n is like p1 power a1 dot 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 pk power ak. And we know that because f is multiplicative, this is going to be p1 power a1 dot 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 f of pk power ak. And because we know that f is the identity on prime powers, so this is like a structural reasoning in math, we know that this is just going to equal to n. Okay, each one is going to equal to p1 to the a1 dot 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 pk to the ak. So just multiplying them all out, and if this was n, p1 power a1 dot 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 pk to the ak, then we know that f of n is equal to n. So we're done. That is a proof of Gauss's theorem, which looks so obvious, but we understood this prime power by prime power, which is a crucial localization concept in number theory, okay? All right, I'm going to show you two major unsolved problems in math that will blow your mind with the Euler Totient function. So the first is based on the following observation that we know in the video, we've seen that phi of p is equal to p minus 1 if p is a prime number. And now there's a conjecture that is it possible, okay? Is it possible, so I'm going to write it as follows, for phi of n to be a divisor of n minus 1 if n is composite, okay? So that's a conjecture, it's called Lehmer's conjecture. It basically asks that for a composite number n, so not prime, is it possible for phi of n to even be a factor of n minus 1? So for p prime, it's equal to p minus 1. But for a composite number, is it ever possible to be a factor of n minus 1? Major unsolved problem in math. So it's pretty cool, right? And the second one is also really cool. It's about solving equations with the Euler Totient function. You're going to love this one. This conjecture is called Carmichael's conjecture. There's basically a theorem of Ford that if you want to find, okay, for each k, so for each k that is greater than or equal to 2, Ford proved a remarkable result. For each positive integer k greater than or equal to 2, Ford proved that there exists an m, okay, there exists a natural number m such that the equation phi of n equals m has k solutions. So in n, okay, so there are k numbers, so that phi of those numbers are all equal to m, okay? We can find exactly, for each k, we can find an m, so there are exactly k solutions in n to this equation phi of n is equal to m. This is Ford's theorem, but what about when k is 1? can you find an m, so there is a unique number n, so phi of n is equal to m? That is a major open problem that is called Carmichael's conjecture. And it basically asks that, does there exist a n, so I can phrase it another way. Does there exist an m such that phi of n equals m has a unique solution? Okay, so this is another major open problem. Both of them are unknown, so they are things to keep you interested. I hope you love this video covering the Euler Totient function. It really gives you a lot of insight because this function shows up so many times in math, especially in number theory, but even outside of number theory, in group theory, in other areas. It's really important to take the time once to just really understand and feel for it. And I hope this video has given you that. And if it has, please don't forget to leave a like and subscribe. And check out the other content on my channel. I've got everything on my channel. I really do everything from beginner to advanced level math. And if you're really enjoying my content, also please consider subscribing on Patreon. There's a link down in the description. There are exclusive perks on Patreon. For example, access to a Discord server where you can chat math with me and other members, plus many other perks such as a personalized thank you message, priority reply to YouTube comments, and so much more. Exclusive updates and news about my YouTube channel. So if you're really enjoying my content and you just want to support, take a look there and please consider having a look there. And I'm super excited to see you in the next video. You're going to love this video. It's going to pop up on the screen right now. It actually calculates the probability that two numbers are relatively prime. And it's very related to the ideas in this video. Check me out in that video. I'm super excited to see you there. Or in another fun video on my channel is going to pop up here. Take your pick and I'm going to see you soon.